So let's next give some justification for why this recursive method for calculating these pi values is correct. And again, I'll use this sentence as an example, and I'll use pi 38 VP as an example. So we're trying to find the highest probability for any VP spanning these words 3 through 8 inclusive. And I'll assume our grammar has these two rules. And in this case, we're going to search through these two rules. And we're going to search for the split point in the range of values 3 through to 7. So the basic intuition is the following. So if I have words 3, 4, 5, 6, 7, 8, if I think of any VP spanning these words, then I have to make some choice of rule. For example, it might be VP prepositional phrase. And I have to make some choice of split point. So let's take s equals 5, for example. What does the split point mean? That means that I'm considering the case where the VP spans words 3 through 5, and the prepositional phrase spans words 6 through 8. So given I choose this rule, VP goes to VP prepositional phrase, and I choose this split point, i.e. I choose this VP under here to span words 3 through 5, the prepositional phrase to span words 6 through 8. The highest probability for any tree which makes those choices is going to be Q of VP goes to VP prepositional phrase, because that's the probability for this rule. And then, as I'll argue in a moment, pi of 3, 5 VP times pi of 6, 8 prepositional phrase. So where do these two terms come from? They come from the observation that for this to be the highest probability tree with this choice of rule and this choice of split point, I have to use the highest probability tree under this VP. Remember, this pi term is going to correspond to the highest probability for any tree under this VP here. And similarly, I have to use the highest probability for any tree underneath this prepositional phrase. That's where this pi value comes from. So to calculate the highest probability for a VP spanning all of these words with this choice of rule and this choice of split point, this is the calculation I'm going to carry out. Now, searching over these different options, the fact that this max is over the choice of rule and the choice of split point just reflects the fact that we're going to search through all different decompositions of this form. We're going to search for all different choices of rules and all different choices of split point, and we'll thereby find the single best way of reaching a VP spanning words 3 through 8 inclusive. So that's essentially the justification for why we can calculate these pi values using the recursive definition that I've shown you here. So here's the final algorithm which puts all of these ideas together. So the input to the algorithm is a sentence, so that's a sequence of n words, x1 through xn, and in addition we have a PCFG which consists of non-terminals, terminal symbols, a start symbol, rules, and a set of parameters. And we're assuming, of course, that this PCFG is in Chomsky normal form. So the first thing we do is implement the base case of the recursion. So for in 1 to n, for each non-terminal, we define pi iix to be q of x goes to xi if that rule occurs in the grammar, and 0 otherwise. That's the base case I'd shown you earlier. In the main loop of the algorithm, we implement the recursive definition I just showed you. And the only thing we need to be careful about is to fill in these pi values for smaller segments before we get to larger segments. And that's what this loop here is doing. So L is essentially going to be the length of the segment that we're filling in. We go for I equals 1 to n minus L, and we set j equals I plus 1. So if you go through this, we're firstly going to set L equals 1, and we're going to try I equals 1, j equals 2, I equals 2, j equals 3, I equals 3, j equals 4, and so on. And then secondly, we try L equals 2. We come back to this. We try I equals 1, j equals 3, I equals 2, j equals 4. So notice here we have segments of length of 2 words. Here we have segments of length 3 words. And so all this is doing is just making sure that we fill in the shorter segments before the longer segments. And that means when we calculate pi ij, we're guaranteed to have these pi values lower down filled in. So this is just applying the recursive definition I showed you. And the only other thing is that, remember, these pi values are just going to store the maximum value for the probability for any subtree rooted at x spanning words I through j. But we really want to recover the tree that achieves that max. And we do this by storing back pointers in a very similar way to the algorithms we saw for HMMs. So in addition to storing pi ijx, I have BP for back pointer ijx, which is the argmax. So this records which rule and which split point actually achieved this maximum value. Once you've filled in all of these values, it's straightforward to use the back pointers to actually trace back the parse tree that is the highest probability tree under the grammar. So lastly, let's talk about the runtime, the time complexity of this algorithm. And it's actually cubic in the number of words in the input sentence. So remember, n is the number of words. And it's also cubic in the number of non-terminals in the grammar. So this is the final runtime of this algorithm. Let me explain how we arrive at this number. If you consider this far into the algorithm, there are order n squared choices for ij. And that's the start point and the end point for the pi value we're calculating. So we have basically order n squared choices for these two variables. And then at each point we have n possible values for x. And for each value of x, we consider all possible rules expanding x. And we have, at most, n squared possible rules, because there's n choices for y and there's n choices for z. And then s is also has at most little n values, because it's in the range I to j minus 1 and I and j between 1 and n. Okay, so we have, this implies, finally, we have n cubed times big N cubed time the final complexity of the algorithm. So again, what I need to emphasize here is this is way, way better than brute force search. Remember, it's easy to come up with grammars where the number of possible parse trees for an input sentence is exponential in the size of the input and the length of that sentence. And so we now have a polynomial time algorithm, which is cubic in the length of the sentence and also cubic in the number of non-terminals in the grammar. So to summarize, what we've seen in this lecture of the course is that PCFGs augment CFGs by simply introducing a probability for each rule in the grammar. And they thereby assign a probability to every possible parse tree under the grammar, where the probability is just calculated as the product of probabilities for the rules in the tree. To build a parser based on a PCFG, you go through the following steps. So firstly, you learn a PCFG from a tree bank. And as we saw, that's really quite trivial. We just read off the rules from the tree bank and then compute maximum likelihood estimates based on simple counts. And secondly, given a new test data sentence, we can use this dynamic programming algorithm, the CKY algorithm, to compute the highest probability tree for the sentence under the PCFG. So that's essentially it. What I'm going to describe next is actually we're going to look at some weaknesses of PCFGs. We're going to give some arguments for why they are really rather poor models for language. When they were initially tried in the early 90s, when tree banks first became available, the results were disappointing. But then we'll see there's some fairly simple ways to augment PCFGs in ways which make them much more effective parsing models, and indeed many of the state-of-the-art models for parsing nowadays are directly based on the ideas of PCFGs you've seen in this lecture.